Swayam Prabha. Digital India. Educated India.
Good morning, friend. Once again, I welcome you to this soil mechanics lecture week 5, and today I am going to start on vertical stress distribution over depth. That means, when you apply load on the foundation, how this below the foundation soil, how it will be stressed, or at any point what will be the intensity of stress, that we are going to find out through this lecture. Will be several of them we may take to go one by one. And now this is actually stress in soils in general within the soil. In the context of geotechnical engineering analysis, we can divide into three important parts. One is stress induced by the weight of the soil above that level. That means, soil may be considered at a depth of 5 meter, but above the 5 meter entire depth of the soil, there will be weight, and that because of that weight at 5 meter depth, there will be some stress. So, that is one, that is because of the self weight or weight of the soil. And fluid pressure, that means when there is a soil is also there is a water table, and then saturated, and because of that level of water table, there will be fluid pressure. And then stress induced by the externally applied loads. That means, this is obvious that we try to transfer the foundation structural load through our foundation to the soil. So, that structural load, how it is transmitted through foundation to the soil, that is another, that is third type, stresses induced by the externally applied load. That means, through the superstructure, whatever load is coming to the soil, that is actually stresses induced by the applied loads. So, these three categories, out of these three categories, we will be soil weight actually is easy to do, which I will discuss later on. At the beginning, I will try to discuss about that stresses because of the externally applied load. And for these we have different theories, and that too these theories, one is Bouguenec's theory, another is Westergaard theories, and they are almost parallel and can be utilized. But Bouguenec's theory is more popularly used in soil mechanics, and this Bouguenec's theory based on certain assumptions, and it has been developed very long back. Actually, it is in 1885, and it is of course, when it is developed for application of some areas, but finally, we have introduced in soil mechanics with certain assumption. Those assumptions may not be truly correct, but to some extent it can be utilized to get some values. So, the assumptions are: the soil mass is elastic, isotropic, homogeneous, and semi infinite. That means, when the load is applied on the ground surface, then ground surface with respect to the point assumed horizontal in infinite both direction, all direction, and also infinite in the downward direction. So, isotropic, homogeneous, and semi infinite. So, laterally infinite, also downward infinite. The soil is also weightless, that is another thing considered, because we are going to do for stress because of the externally applied load, not because of the self weight. So, because of that, the theory is assumed that the soil is weightless, and load is a point acting on the surface. It is a point load, in fact, there is a typo error. This is a point load acting on the surface, and with this assumption, in fact, the entire derivation is out of the scope of this course, because we are, as a user, we will be using the Bose-Einstein theory, and here actually initially when it is developed, the Bose-Einstein theory, it was actually in a rectangular coordinate system x, y and z, and we can consider at a point x which is point any point at a depth z which is at a distance x from the y axis, y from the x axis, and at a z from the xy plane. So, this is the point, and this point is shown in a little enlarged exaggerated one, and you can see this point, if I consider as a solid of 3 dimensional solid, then we will get 6 planes, and each plane there will be a number of forces acting, normal and shear. Normal will be 1 perpendicular to the plane, and shear will be 2 parallel to one plane, parallel to one axis and perpendicular to the other, like that this one and this one both shear stress will be there. Similarly, this plane, similarly this plane. So, all those planes there will be shear and normal stresses, and directly we will be going to we are going to I am going to the expression by which these stresses can be calculated. So, here this is given sigma z expression 3 q by 2 pi z cube by r to the power 5. This r is what actually here it is shown. You can see this is the r, this is the r. Okay. So, you can find out this small r as under root x square plus y square z square, and this is again z. So, this r square plus this z square ultimately will be under root x square plus y square plus z square. So, this is the one, sigma z is given this, sigma x is this, sigma y is this. These are the expression for different component of stresses. Similarly, these are all normal stresses, and next this one is shown all normal shear stresses tau z x, this is the expression, tau x y, this is the expression, and tau y z, this is the expression. So, this was originally in a rectangular coordinate, and now later on it was converted to polar coordinate to reduce the number of variables, but with some assumption that solid should be circular. So, in that case in this, if it is a polar coordinate system, then one variable is r, another variable is z, and same thing can be converted, r is nothing but under root x square plus y square. So, r and z, with respect to r and z, if this is explained, this is expressed, then those equations or stress components reduces to some other form, and they are given like this: sigma z equal to q by 2 pi z square 3 cos cube theta, and this theta cos theta is somewhere here it is shown. So, this is the theta. So, this is the one, and this theta value if I substitute by this and this, and then this one will be reduced to some other form. So, that I will come later on. So, this is actually sigma z that in terms of theta shown in the previous figure. Similarly, sigma r, that means radial direction, there is a component, sigma t, there is a tangential, there is a component, and there is a tau. So, all those stress components are there, but out of these generally we apply load vertically, and this vertical load always will be created significant large value of stress, vertical stress, and this vertical, because of this vertical stress there will be soil compression will take place, and this actually we generally frequently use for the sigma z. So, because of that I will just other stresses it is not that other stresses are not important, but the sigma z value or magnitude is large, and because of that I am trying to concentrate more on sigma z. In soil mechanics actually in subsequently we will see many areas you have to calculate for sigma z component, sigma z, but that force applied at a surface, and then at a particular depth what is the value of sigma z to be obtained, and that z actually finally has to be used for some other calculation. So, because of that, and that is frequently used, we will show you subsequently this application. So, because of that I am concentrating more on the sigma z, and as I have shown that sigma z in the polar coordinate system, it was shown in terms of cos theta, and cos theta if you substitute and simplify, then it will equation will be reduces to 3 q by 2 pi z square 1 by 1 plus r by z square to the power 5 by 2. So, that means it is typically it is like this. If it is force is applied here and suppose your point is somewhere here and that is at a radial distance r and at a vertical distance z, then you can see this is the vertical depth z and radial distance r, and so these are the two things are kept here, and load suppose is suppose when load is acting here at a radial distance r and vertical depth z, what is the value of or what is the expression? So, if I apply a q load here, I will get sigma z here, delta sigma z I will get here by this expression, and what is this q is this one applied, and what is z this z, and what is r this is the r. So, that means, if I know these three things, then I can find out the stress at the at a particular depth. So, now I can say as two variables are there, one is r, another is z, and because of that you can see here if I fix the value of r, that at a particular distance of load is applied here and I have taken at a some distance about 2 meter, and then I vary z, then over the depth how this vertical stress is varying. So, now you can see r is fixed constant kept constant, and then over the variation of z the vertical stress is varying like this. That means, close to the surface it is less, and at some depth it will be increasing reaching to the maximum, then it will be decreasing, and it theoretically it is supposed to go up to the infinity, but up to some depth the value when compared to the maximum value become negligible, we generally ignore the effect. So, this is one observation. Second observation is when we suppose a z is fixed, that means I want to find out at a point load is applied at the surface, but I want to find out a 2 meter depth and from any distance from the point of application of the load. So, both side if I go. So, that is the case, suppose z is fixed suppose at 2 meter or 4 meter, and with the variation of r, this direction r is increasing, this direction r is increasing, and you can see below the load you have the maximum vertical stress, and when you will go up away from the load, then your stress is decreasing. So, this is another observation, and now next one is if I now show with respect to three different depth, suppose you can see now. Now, we have considered at 3 different depths or 4 different depths. So, this is at z 4 meter, suppose 1 meter, this is at 2 meter, 3 meter, 4 meter, but you can see that the variation or trend is similar. That means, is the maximum at the below the load is applied suppose here, just vertically below the load is the maximum stress, and when you go away from the point of application of the load, the value is reducing, and this trend is same as it is in 1 meter and it is or whatever depth. But finally, what we will another thing is, that is one thing, that is maximum value is at the below the load and less value when you go away from the point of application, and with the increase of the depth this peak value also decreasing, and also this entire value from the away of the point of application, that value become negligible if you go deeper and deeper. So, these are the trend we can see. So, this actually we are not doing anything, simply whatever equation point load equation we have got, by using that point load equation, if I change r and z, once you keep r as constant, vary the Z, then you will get the trend that how it is varying the vertical stress over depth, and then once you can keep Z is constant and then vary R, same equation, by the same equation, that is actually your del sigma equal to 3 q by 2 pi into Z square into 1 over 1 plus R square by Z square to the power 5 by 2. This is the equation only we are using, but once I am keeping this constant, vary this, I get the result, or I keep this constant and vary this, then I will get another trend. So, this is the, by doing this I have tried to show these two things, how if I apply the load at this point at 2 meter distance, 2 meter away from this, how much is the stress, and at the same time at 5 meter depth, what will be the stress that can be obtained by this. Next one, since I can see now, I can go back to this previous one, and these are the stresses, stress distribution. Actually, this is a stress distribution at some depth, this is a stress distribution at some depth, this is the stress distribution at some depth, like that. And now we can see that since with the increase of depth, stress is decreasing, and with the increase of R, stress also decreasing. So, we may get a several combination of R and Z, where we can get the intensity of vertical stress is same. So, that is the thing. So, maybe intensity of stress here and intensity of stress here is equal, because you can see here, here actually R is less and here is Z is less, but R is more. Here actually Z is more, but R is less. So, because of this, and but a particular combination, this point whatever stress, this point also stress is same. Similarly, this point also stress may be same, this may be, this point also stress also will be same. Similarly, I may find that at this point the whatever R and Z, this point the R and Z different, and if you apply to this equation, you may get this value are same. Similarly, this value and this value also same, this value also same, this value also same. So, like that, in when I apply a load on a ground surface, and then I will get a several point like this, like this, like this, like this, like this, like this. Maybe this is actually this point and this point R and Z same, but this point and this point R and Z same, but they are different from here. So, as a result, we may get the stress value equal, it will be like this, suppose. Similarly, I get another set, I will get something like this, equal stress. I get another, I may get equal stress like this. So, those actually, that means below the load point we will get several points, those points with several combination of R and Z, where we will get the equal vertical stress. And if this equal vertical stress, then that is called actually your pressure bulb. Actually, in the soil mechanics, this is we use this term as pressure bulb. That means, what is this pressure bulb? This is actually the line joining the pressure of equal magnitude, that is called actually your pressure bulb. And this pressure bulb, finally, I will show you later on that this, when the pressure bulb which is close to the load, the intensity is more, and when you go away from the load, the intensity will be smaller. Suppose here actually you are getting 0.1 q or 0.8 q, suppose q, and then you will get, suppose this is 0.1 q suppose, and if you go further you may get still smaller, and but theoretically speaking up to infinite depth you will get this type of pressure bulb. Now, in soil mechanics we suppose if I apply a load at the surface, up to what depth it will consider, that means soil under loading it will behave differently, and because of that soil may go undergo compression subsidence, and because of that you have to consider up to certain depth of soil, and so up to what depth we have to go. So, that is what I will show you later on, that if I apply a stress magnitude of suppose q, and at a particular depth when this pressure intensity become less than 0.1 q, less than 0.1 q. Suppose I have applied q at the surface, and at a particular depth it become less than 0.1 q, and so that is what we consider in soil mechanics or geotechnical engineering as a depth of significance or significance depth. What is the meaning of it? That means up to this depth we should know all details about the soil, if there is any layering, if there is any variation in soil strength, soil properties, etc. You have to invest. That means, when you do soil investigation, then we have to do at least up to this significant depth. You may go deeper and deeper to get more information, but at least you have to do up to this. So, this is the calculation by which we can get up to what depth we have to do the investigation. So, like this, so this is actually some application of Bouguenec's theory by applying when applied a load at the surface at different depth, what is the intensity of vertical stress we can calculate. Also, we can find out up to what depth we need to investigate the soil, so that we can design the structure over it, considering the variability in the soil. So, this is the one, and with this I will close this module. Okay, thank you.